So today, we're diving into a really fascinating new way to think about how we give an AI its goals. It's called dual goal representations, and honestly, it might just be the smarter GPS that artificial intelligence has been waiting for. Let's get into it. All right, let's start with a really basic question. How do you actually give a robot a goal? How do you tell an AI agent, hey, this is what I want you to do? It sounds simple, but this is one of the most fundamental challenges in all of robotics and AI. You see, this whole field is basically trying to teach an AI how to reach any target you give it. But giving that AI a useful sense of direction, well, that's way, way harder than it sounds. Now, the way we usually do this is pretty intuitive. You just show the AI a picture of what you want the end result to look like. Here's an image of the cup on the table. Go make the world look like this. Think of it like dropping a pin on Google Maps. It's simple, it's direct, and you'd think it would work perfectly. But, and this is a big but, there's a huge problem with just using a single point on the map. In the real, messy world, that simple coordinate is packed with confusing information that can send an AI completely off the rails. And this really shows you what I mean. On the left, you've got the ideal goal, what an AI might see in a clean, perfect simulation. But on the right, that's reality. The lighting is different, the background is cluttered, maybe something moved a little. An AI can get totally bogged down in all that irrelevant visual noise. So this boils down to two massive problems that researchers wanted to solve. First, these simple goals are just full of extra, unhelpful info, all that background noise we just talked about. Second, and this is so important, a single picture of the destination tells you absolutely nothing about the journey. It's completely missing the context of how to get there. Okay, so this is where the big idea, the aha moment, comes in. What if, instead of defining a goal as a single, isolated point, we defined it by its relationship to everything else? What if we could build a totally new kind of map? To build this new map, we need a new ruler. We're not measuring in feet or meters. We're using something called temporal distance. Simply put, it's the shortest possible travel time between 2 points. How many moves would it take a perfect agent to get from point A to point B? That number, that's the temporal distance. So just to be super clear, the old way treats a goal as just this, one single, isolated dot on the map. And this is where the researchers took their inspiration, from a deep, core idea in mathematics. This quote really gets to the heart of it. An object, or in our case, a goal, isn't just defined by what it is in isolation, but by how it relates to everything around it. And here it is, the new way. A goal is no longer a point, it's a web. It's a unique signature, a fingerprint made of travel times. You can identify any spot in a maze, not by its X and Y coordinates, but by a list of how long it takes to get to that spot from every other spot. That list of relationships, that becomes the goal's true identity. Now, a map like this has two incredible properties. We're calling them superpowers here. First is sufficiency. Because it's literally built from travel times, it already contains all the info an AI needs to figure out the best path. And second, noise invariance. Since it's based on the physics of getting around, not the messy visuals, it automatically tunes out all that distracting background stuff. Okay, that's a beautiful theory. It's really elegant and it makes a ton of sense. But the big question is always, does this new map actually work better in the real world? Well, the researchers put it to the test. First up was a classic puzzle called Lights Out. On the left, you've got the success rate using the traditional goal, about 50%. Not too bad, but look at the right. The AI using the new dual goal representation, a perfect 100% success rate. That's a huge leap, proving that this relational info makes learning way, way easier. But puzzles are one thing. What about messy, complex robotics tasks? They tested this on 13 really tough challenges. Using the dual representation method, the AI scored an average of 41. So, how does that stack up against the standard approach? Well, its average score was 34. So yeah, across a whole bunch of different hard tasks, this new way of defining goals gives a clear and really consistent performance boost. It's a pretty big deal. Okay, it's definitely better, but what about that noise invariance superpower we talked about? Does it really hold up when you start throwing distractions at the AI? Well, they tested exactly that. They took the tasks and started adding random visual noise to the goal images, basically trying to trick the AI. And look what happens. The standard method's performance just tanks. But the dual goal method, it maintains a much, much higher success rate. It's way more robust, proving the theory was right. It really does ignore the noise. So what's the big picture here? What does this all mean? This isn't just some clever programming trick. It's a fundamental shift in how we communicate our intentions to an AI, focusing on relationships instead of just lonely, isolated points in time. So let's just recap the journey real quick. We started with the problem. Simple map coordinates are fragile and get confused by real-world mess. Then came the big idea. Redefine a destination by its travel time from everywhere else. And the result? A much smarter, more robust agent that truly understands its objective on a deeper level. And you should know, this is not just an academic exercise. This is a huge step towards creating the kind of adaptable, general-purpose AI that we need to operate reliably in our messy, unpredictable world, whether that's a robot in a factory or a self-driving car on the highway. And that leaves us with one last big thought to chew on. We've always defined things by what they are. This whole idea forces a new perspective, defining things by how they relate to everything else. If we can teach our machines to see the world this way, through a web of relationships, what incredible new perspectives might they, in turn, show us?